Okay, in today's video lecture, we want to talk about pulse width modulation. Most people just call it PWM, and it's part of what's called the output compare modules. And it's about generating a continuous square wave. So here's a square wave. You have to think of this continuing on forever. We talk about the on portion and the off portion. This gives you the period of the PWM signal. It keeps repeating in this time. The on time is often called the duty cycle because that's when it's working. And people frequently talk about a percentage duty cycle, the ratio of the on time to the entire period, times 100%. So this looks something like maybe 30%. Okay. PWM, or these square waves, are used to control a lot of things in electronics, and we'll explain the many uses a little later. So as I mentioned, we have 5 modules that can generate this continuous square wave. They're set and forget, which means once you set them, the pins output the signal and you don't have to do anything else. So your program can do anything else while these signals are called. Mind you, in your program, you can change the settings as well, which can come in useful. Okay, the pins are called OC1, OC2, OC3, 4, and 5. If you check out your pin out diagram, there are no such pins labeled. And what that means is you have to use the reprogrammable pins, right? So they have to be associated and turned into digital output pins as well. So that's a bit of code we're going to need in any program. So what are the uses? Well, we've been blinking an LED and almost manually, right? We tell it to turn on, tell it to turn off. But you could set up a little piece of code to generate that blinking LED with no problem using PWM. If you take a blinking signal and send it to a speaker, well, it's actually going to generate a noise on the speaker. Okay, and so we'll do that because they're simple things to do. But mainly, the main use of PWM is a control. For instance, the speed of motors is usually controlled by PWM. But you can also do things like brightness on an LED and the color. You saw how flashing things, 2 different colors can give you a third. Okay. So let's talk about LED blink and brightness. So this is something we've already done with our 2-color LED. If the period is long, you can see something turn on and off. But if the period is short, you see a blend of the 2 colors. I'm going to show you some animated GIFs or GIFs so that you can see the difference here. So here's one of them. This is a red rectangle and a green rectangle just flashing back and forth. The delay is long enough is that you always see it as red and green. I'm going to change, I have another animated GIF with the blink rate much faster. And to me on this screen, but maybe the video won't show it as well, this is often sort of brownish looking, okay, or amber looking. And that's because my eye is seeing a blend of red and green. Okay? And you'll play around with bicolor LEDs to see what kind of behavior you can get. Okay, so that's how I'm changing the color. So a bicolor can give you 3 colors actually. On the other hand, if you have a large duty cycle, 1 pin and for an LED going to ground, it'll be mostly on. So an LED would be fully on, so bright. But if the duty cycle, the on time and then the off time was long, then it would appear pretty dim. So you can use PWM to control the brightness of an LED. You can also use this to control the speed of DC or direct current motors. Now, for a long period, you see start, stop, right? So you turn something on, moves a little, then it'll stop, come back on, stop. But if you look closely, that behavior is a little more complicated, because when you turn a DC motor on, it takes a little while to get it turning. And when you turn it off, then you're going to see it take a little while to slow to zero. That's called inertia. With a small duty cycle, we find that the average speed is lower than with a large duty cycle. So by changing the duty cycle, you can change the speed of a DC motor. And in fact, if you use a second pin, then you can control the speed of rotation as well. Let's go into a bit more detail with this. So this is my square wave signal. And if it was an ideal motor, the motor would only be on here, off here, on here, off here, on here, and so on. But what really happens is it takes a while for the motor to get up to full speed. If we turn it off, it takes a little while for the motor to go back to zero. So you're getting this sort of shark fin approach. Okay? Now, these are fairly long on and off times. If I shorten them up, right, then in that short amount of time, when it's on, the motor doesn't get up to full speed. And similarly, when you turn it off, it doesn't necessarily get to zero. And if you imagine taking those little pieces and repeating, then what you get is this ripple here. Okay? And that ripple can be quite small, be unnoticeable. It'd be almost like a flat line. Right? Up here is the maximum velocity. That would be full speed. So we're roughly about half speed here. So we can make a DC motor go at different speeds. Let's look a little at sound generation. Right? You might recall that a pure tone is a sine wave of different frequencies. A square wave approximates that. I know this doesn't look like a square wave. This is a nice sinusoidal wave, but it's good enough for what we want to do. It might not sound that good, right? But if you're trying to generate noises, that's great. Remember that frequency is 1 over the period. So if you know the frequency of sound you want to produce, say 200 hertz, then the period is 1 over 200 hertz. If you want to do music, you should know the frequencies of the different notes, A, C, G, etc. Okay? And that's it for sound generation. Let's now talk about how the module works. Okay, so there's 3 elements. You need the peripheral bus clock, because that does the timing, but it just keeps, it's sort of like the heartbeat of the modules. You need a timer counter, and what that does is it keeps a count of how many edges, rising edges, that is counted. Right? So that's how you set the period, essentially. And then you need a second counter, right, which is part of the PWM module, that says, oh, you've reached the count for the duty cycle, turn off. Okay? So 3 parts: the background clock, a counter that's called the timer counter, and a counter for the PWM signal. Okay, so let me say I set the period of the PWM to 5. Actually, I'm setting it to 6, when I'll show you in a moment. Okay, and the duty cycle to 2. So here the timer is started. So this is the first rising edge, this is 0. Okay, if I count up 1, 2, 3, 4, 5. I've set the period to 5. Well, it looks like the period's set to 5. But this rolls over now to 0. This would have been 6. And you can see we actually have 6 intervals. So I'm not counting 5. I'm actually counting every 6 intervals. So this is 0, 5, 0, 5, 0, 5. So on the 0, the PWM turns the pin high. And it's got its own counter that looks at when the counter goes to 1, 2. Right? Start the signal again, 1, 2. Right? All like that. So the duty cycle is 2, but the period here is 6. So the percent duty cycle is a third, or 33%. So let's look how we would do that. We've got two possibilities here. We can use a 32-bit timer or 16-bit timer. Let's start with the 16. Okay, so here's the counter, open timer 2, that counts the peripheral clock, and we're turning it on. We're using a scaler of 1 to 1. Okay? I could have used different scalars. Instead of counting every first edge, I could count, say, every 8th edge back in that signal. Okay? And here's what's called the period. We're setting the period to 5. In PWM, I have the choice of either using timer 2 or timer 3. Those are the only two timers that will work with the PWM mode. And you have to tell PWM. Okay? This is 16-bit, the period, so it goes from 0 to 65536, which is 2 to the 16 minus 1. Right? So 0 to that number, 2 to the 16 choices. Okay, so we've got 5 pins. Remember, you had to configure which pins you're using, right? And typically you start off with closing the module. I know that sounds strange, but what that does is it clears all the registers that control output compare. So you're back at the default mode and nothing's hanging over. Okay. So here, all in gray is most everything that we won't change, turning it on, saying we want the PWM mode, right? Using 16-bit, okay? And here it's saying use timer 2 and give me a duty cycle of 2. And again, this is a 16-bit number. This last number is always 0. We're not going to use it. Okay? Now, this is a fairly complicated piece of code. You could keep writing it out if you want to keep changing the duty cycle. But there's a secondary function that once you've opened the output compare module, you can always change it if you want later. I'm going to show you an example of that code. So here it is with 2 PWM timers set up. Okay, so here I'm setting up 2 pins as OC1 and OC2. They're digital output, so I'm making sure they're digital output. Sometimes the modules will take care of that, sometimes they don't. It's always safe to do both of them. So I'm going to use timer 2 for the first one and timer 3 for the second. Okay. If I use the same timer for different PWM, then they have to have exactly the same period. These guys can have different periods as a result. So here's all my examples, right? So this is the period. Okay? And here we have all the code, right? Almost identical to one another, just using a different duty cycle for these guys. Okay? So the period here is 30,000 times 2 instruction cycles. Okay? Well, 30,000 plus 1 because of that rollover effect. Okay? And so usually when I write this code, I'd use something like 29999. So plus 1 would give me a nice, simpler number to work with for my period. Okay. And let's come down here, right? So this is going to be period here is 20,000 plus 1 times 4. I don't like that. Okay. So let me go back and talk about the 32-bit. Okay, we can only use one timer here. That's the blended 32-bit timer, which is timer 2 and timer 3 chained together. Okay, now we can have much bigger range of numbers. So it would be overkill to be using this with 5. You'd use a 16-bit timer. Okay. Here we've told it to use a 32-bit timer, and for 2, 3, you still call this 2. And again, you can have much bigger range here. So almost identical. And I can show you the code for that as well. No, I can't. I don't have it set up, but it's very similar. I'll grab that in. So here's the 32-bit case. Again, configuring the pins to work. I'm using OpenTimer 23. We'll talk about a bit more about OpenTimer and timers in general in the next lecture. And here I'm using OC1 and OC2. These two numbers can be quite big, and you can see this, I chose a much longer period here. These guys have exactly the same period for the two pins, right? And again, I can change the period anytime here after a 10-second wait. Let's go back and look at how we do some calculations that are important. The PWM time is equal to the period you give plus 1, the period in the timer, okay, because of that rollover, times your prescaler, which could be like 1, 2, 4, 8, 16, 32, 64, 256, times whatever the instruction cycle is for the peripheral bus clock. The duty cycle time, whatever the duty cycle number was, right, times the prescaler times the instruction cycle time. And here's some calculations from the problems we just did. Right? So 30,000 plus 1 times a prescaler of 2 times 1 over 8 megahertz. You get a fairly funny number, which is why I would have chosen usually something like 29999 plus 1, so that you get less funny numbers. The duty cycle, 22,000 times 2 divided by 1 over 8 megahertz. Right? And similarly, for the other ones where the prescaler was 4. Just want to mention one last thing before I leave this topic. In the PWM signal, if the period is long, right, and you call the second signal, right, later in the program than you call the first one. So here I'm calling PWM2. The second signal doesn't start until the next rising edge of the signal. Okay? So let's keep that in mind if this is a long delay. That's all for now. Thank you.